Let's talk about the magic of memory protection. In the late 50s and early 60s, programmers had a huge problem. They could just run a single program on a computer at once, and this was extremely wasteful. For example, if a program needed input, the CPU just stopped processing and waited for the input. And input was really slow. And the worst part is, these idle times were extremely expensive. Depending on the machine, the hourly rate could be up to $450, and that's $5,000 in today's money. So they had to find a solution.
The idea was simple. Whenever a process is waiting for input and has nothing to do, the CPU simply switches to another process instead of idling. But this quickly introduced another set of problems. So a straightforward way to switch between processes is to give each process full access to memory. And if it has idle time, we save its state on some kind of disk and load another process. But saving a program's state on disk is really slow. See, a CPU operation takes about a nanosecond. Accessing the CPU's L2 cache takes 10 nanoseconds. Accessing RAM takes 60 nanoseconds, and accessing a disk takes 5 milliseconds. And to better understand what that means, let's take a different perspective. Let's say a CPU operation takes a second. Then on this time scale, accessing RAM takes a minute, but accessing disk takes a month. So it would be way better to leave the processes in memory while switching between them. But unfortunately, this introduced yet another set of problems. One particularly important issue is that of memory protection. So we certainly don't want that a process is able to read or write something into another process's memory space. And at this point, we're not talking about some type of hacker attacking the system, but it could easily happen due to programming errors. So they needed a solution, and the solution at the time was base and bounds. But what is base and bounds? Well, in base and bounds, we have two CPU registers. One is called the base register and the other the bounds register. And both together define a memory region. So the base defines the start of the region and the bound defines its size. For example, if we choose this address as the base and 4 kilobytes as the bounds, we get this region. Okay. So all the magic of base and bounds is done by a part of the CPU called the Memory Management Unit, or MMU. And what it does is the following. If we set the base register to some value, any address that we provide through our code is calculated relative to the base. For example, if we try to access this address while the base register is set to this value, we don't access this area as we would without base and bounds, but this. So each physical address is now calculated like this. And the address we provide in this case is called a virtual address. And all the calculating is done automatically by the MMU, so we don't have to do anything except setting the base register. But how does that help us with memory protection? Well, that's where the bounds comes in. So the MMU also checks whether we are within or outside the defined region. And to do this, the MMU checks whether the virtual address we provide is larger than the bounds. And if it is, we would try to access an address outside our region. And the CPU raises an exception. For example, if we try to access this address, the MMU finds that the address is not larger than the bounds and allows the access. If we, on the other hand, try to access this address, the MMU recognizes that it's larger than the bounds and raises an exception. But how can we implement memory protection with that? Well, what we could do is to simply define a separate region for each program. And then, before we run a program, we set the base and bounds registers to the program's region. And if the program then tries to access memory outside its region, well, it fails to do so. So perfect, right? Well, as you might have guessed, base and bounds also has its problems. But what could that be? Well, let's take a look at how a program typically looks like in memory. So usually we have the code, the heap, and the stack. Now, between the heap and the stack has to be some unused space, just because they need some space to grow. But with base and bounds, we have to store the entire program in one piece. So we have to reserve this space, even if we don't store anything there. And that's quite wasteful, isn't it? But again, there's a solution for that. And that's segmentation. Segmentation was developed in the early 60s. But how does segmentation solve this problem? Well, segmentation is a generalization of base and bounds. Instead of having only one base and bounds register pair, we now have several segment registers. For example, in x86, we have these 6 segment registers. And each of these segments works exactly like the base and bounds registers. So with each segment, we can define a memory region just like before. So having that then allows us to put each program segment into a different location. And by doing this, we don't have to reserve any unused space. And by the way, you've heard the term segmentation fault, right? Well, that term comes from an illegal memory access on a segmented machine like we've talked about. And the term still persists even on machines where no segmentation is used. But how is segmentation implemented? Well, let's find out. Despite being the third part of this kernel dev series, this part is understandable on its own. So if you haven't watched the first 2 parts, no problem. But if you want to know how we got here, take a look at my kernel dev playlist. Alright, let's see how segmentation is implemented. Now, this manual will be our best friend. And it only has a lean 5,000 pages. And to implement segmentation, it says we only have to implement this. Pretty obvious, right? Well, don't worry, you will get this when we're done with this chapter. And by the way, when I first read this manual, I was completely lost and it was pure suffering. But after you get used to it, it's easier than you might think. So from now on, our only commandment will be read the manual. Okay, how is memory organized in x86? Well, the memory that the CPU addresses on its bus is called physical memory. And physical memory is organized as a sequence of bytes, so 8-bit chunks. Each byte is assigned a unique address called the physical address. And the physical address space in a 32-bit system ranges from 0 to a maximum of 2 to the power of 32 minus 1 bytes. So, how is segmentation implemented then? First, we need a global descriptor table, or GDT. The GDT contains the descriptions of the segments that we want to use. Each entry within the GDT is called a segment descriptor. And the segment descriptor defines, for example, the base address or the size of the segment. But it also defines a lot of other stuff which we'll discuss later. Alright, let's implement that in C. This is where we left off. First, let's create a header file and a C file. Then, let's define a struct for the segment descriptors. And it's important to give it the packed attribute, because without that, the compiler may add padding, that is empty space, between the data. And that would be bad, because the CPU expects the data to be contiguous. Okay. But what data must a segment descriptor contain? How do we find that out? Yeah, the manual. So here we have it. I know, pretty straightforward, isn't it? But again, you will get this in a minute. This looks harder than it actually is. So, the segment descriptor is 8 bytes long. But before we get into the details, let's just copy what we have here to our struct. And because x86 is little endian, we have to start here. That is, with the least significant byte first. Okay, let's do that in C. And then we get this. And this is really just a copy of what we've seen before. Now we have to fill it. And to do that, let's first create the GDT table itself. We use 3 entries for now. And for the table itself, we just define an array of segment selectors. And then we need a function to fill the GDT. So as arguments first, we have an index, which is the position within the GDT. And then we have the base address. And this is where it gets a little messy. So the base address is 32 bits long, but for whatever reason, maybe some compatibility issue, it's not placed in one piece into the descriptor. We have to chop it up and place it here, here, and here. So let's say we have this as our base address, then we have to put this part here, this part here, and this part here. And in C, we use a bunch of bit level operations to do that. And then we get this. Okay, then let's talk about the limit. And this is even worse. Why? Well, let's take a look. So note that the function takes the limit as an unsigned 32-bit integer. Now, the limit is the size of the segment. It's exactly like the bounds, except we now call it limit. And like the base, we cannot put it in one piece into the descriptor. We have to cut it into two pieces and put it here and here. But unlike the base, it has quote-unquote a weird size, namely 20 bits. And I say weird because we cannot divide it into bytes. That is, it's not divisible by 8. And that makes our lives, well, a little harder. So recall that the function expects a 32-bit value. So for example, a value like this. But because the limit is only 20 bits long, we have to throw away 12 bits. And it's best to throw these away. Then this part goes here, and these remaining 4 bits go here. Let's implement that in C. To place the first part, we can just isolate the lower part of the limit using bit level operations. But the remaining part is a bit problematic because we cannot just store 4 bits. We have to store bytes. So we have to include the flags here. These are also 4 bits, and together with the limit, we have a byte. And as flags, we have the granularity flag. And when this flag is set to 0, the limit is measured in bytes. And when it's set to 1, the limit is measured in 4 kilobyte units. And that means if this flag is 0, the segment size can range from 1 byte to 1 megabyte. And when it's set to 1, the segment size can range from 4 kilobytes to 4 gigabytes. Then we have the default operation size. This flag should be set to 1 if we are on a 32-bit system, which we are, so we set it to 1. And this flag is only relevant if we use 64-bit, which we don't, so we set it to 0. And the AVL flag is for us. The hardware doesn't use it, so we could use it for any purpose, but we don't, so we set it to 0. Now, in C, we pass the flags as an 8-bit integer. But the flag itself is only 4 bits, so we have to isolate the lower 4 bits. And we have to also put the limit bits into the right position like this. Now what's left are the access bits. And in the code, we already have them here. Luckily, they are easier than what we had before. We can just place them as is. And the access bits contain the following. The segment present bit. When this bit is set to 0, the CPU generates an exception when we try to use the segment, so we set it to 1. Then the descriptor privilege level. We haven't talked about privilege levels yet, but we will do so in a future video. For now, let's just note that the CPU can run in different privilege modes and that we can use them to grant access or not. So we don't worry about that today and just set it to the highest privilege level, which is 0. Then we have the descriptor type. And because we only talk about code and data segments in this video, we set this to 1. And finally, we have the segment type field. And this field defines whether the segment is a code or a data segment. So code segments are executable and data segments are not. And in this table, we can see what config options we have. All right, great. Now we have the ability to create a GDT, but the CPU doesn't know about it yet. So we have to tell it where it lies. And to do that, we have to load the address and the size of the GDT into the so-called GDTR register. So first, let's define a struct for the GDTR. And like before, we have to use the packed attribute. And then we write an initialization function. Within that, we set the limit, and the limit has to be the segment descriptor size times the number of segments minus 1. And then we set the address. Then let's define two segments. And to do that, we first have to set a null descriptor. So we do that, and then we define a code segment like this and a data segment like this. And both of these segments start at 0 and go up to 4 GB.
Now, the only thing left to do is to load the GDT. But how do we do that? Well, there's a special CPU instruction for that, the LGDT instruction.
To use it, let's set up a function in assembly. First, let's create a file and define the function. And in our minds, we already plan the function. So it will take the GDTR address as its argument. And according to our function calling convention, the argument will be at this position on the stack. So we get it and store it into the EAX register. And then we can use the LGDT instruction. And this instruction expects the GDTR itself. So we have to dereference EAX. Okay then, let's call the function from the init function, add all the function declarations, modify the makefile and fix typos. And finally, we can call the init function from kernel main. And now we're ready for testing. And to do that, let's compile our kernel, and then we run QEMU with these S flags, which allow us to debug with the debugger GDB. So after starting, QEMU pauses and waits for us to connect to GDB. So we do it like that, and then we add a breakpoint at the GDT init function, and then we let it continue until it stops right before the function. Now let's inspect what is set as the GDT. And what we find is that there is something set. This could be done by, for example, GRUB, but it's definitely not what we implemented. And we know that because this is not the length of our GDT. Alright, so let's continue a couple of steps until we hit the end of the GDT init function. And now let's inspect again what is set as the GDT. Well, something happened here, so that's good, but this is our GDT. Well, let's check by comparing the length and address. And this matches, so perfect. But we still have no memory protection. Well, let's change that.
To run a somewhat realistic test of memory protection, we want our kernel to be able to run programs. But our kernel is not really able to do that yet. Luckily, GRUB has a feature that can help us here. And that feature is really useful even beyond this specific application.
First, let's write a simple program and let's pretend this is a banking program that stores sensitive account data. Then we need a linker file. And for now, let's hardcode the program's address like this. Now, to load the program, we include it as a GRUB module. And because GRUB modules are not the topic of this video, I skip a detailed explanation of how this works. The important part is that we can provide a flat binary to GRUB and then easily run it from our kernel. Okay, let's test the program. And remember, it only prints the secret data to the screen. And as you see, it works. Now, let's get back to segmentation for a moment, because we learned how to define segments, but not how to use them. To activate a segment, we need to set a so-called segment selector. And the segment selector is a value that we load into a segment register. And this value then tells the CPU which segment descriptor to use. And then the flow goes like this. If we want to access memory via a segment, first the CPU uses the segment selector to locate the segment descriptor for the segment. Then the CPU examines the segment descriptor to get the base address, but also stuff like access rights. And finally, it calculates the physical address from the base address and gives access if it's allowed. So here is what we have right now. First, in memory, we have the kernel and the banking program, and as segment descriptors in the GDT we have at offset 0, the null descriptor, then at offset 8 a code segment that covers the entire memory space, and if this segment is activated, we can execute and read what's within the segment, and finally at offset 16 a data segment that also covers the entire memory space. And if this segment is activated, we can read and write what's within the segment. And by the way, the offsets are just the result of the fact that each descriptor is 8 bytes long. Okay, let's activate these segments. And to activate a segment, as we've seen, we just need to write the so-called segment selector into a segment register. And for our purposes, we can just say that the offset is the segment selector. In reality, there are some additional flags in the selector, but for now, we just set them to 0. Alright. In x86, we have these 6 segment registers, and each segment register has a specific purpose. For example, we have the code segment register that is used for instruction fetches. We have the stack segment for stack operations, the data segment for data accesses, and additional segment registers for general purposes. And we now just set them in a very simple way. The CS register is set to the code segment and all others to the data segment. And then we'll build on that. Okay, let's implement that. So all the registers except the CS register can be set by using a simple move instruction. But the CS register is different. Here we have to use a so-called far jump. A far jump sets the CS register, but also changes the instruction pointer. Okay, let's test whether everything worked. And to do that, we use GDB again. We set a breakpoint at the GDT init function and inspect the segment registers before and after execution. So, here is how it looks like before we set them. They just have some values, maybe set by GRUB. And here, after execution. And these are exactly the segments we defined. So that's quite nice. And now we need an evil program that steals data. So let's write one. So this program reads the memory region of the banking program and stores what it has read in a file. But of course, it could also easily send it anywhere. And let's also briefly write a linker file, and like with the banking program, we hardcode its address. Okay, let's test it. So we run the banking program first and then the evil program. Alright, let's run it and then let's take a look at the file. And oh no! The evil program was able to steal the data. That's something we cannot tolerate. So let's protect the banking program's memory. And to do that, we add 2 further data segments. One for the banking program and another for the evil program. Then, before we run each of these programs, we set these registers to the program's data segment. For example, when we run the evil program, we set these registers like this, and then when the evil program tries to read data outside its data segment, the CPU raises an exception. Alright. Let's define the additional segments in the GDT init function, and then let's first test the segment for the banking program. And to do that, we set the segment registers before the program is run, and afterwards we reset them to their original state. We also have to modify the banking program a little, because the write-to-screen function makes a memory access that breaks when we use the data segment. So instead, we let it output text to a file. Then, in the linker file, we have to change the address to 0. And this is because now addresses for data accesses are calculated relative to the segment base rather than as absolute addresses. Okay. Let's test it. And what we expect is that everything works like before. And it does. Nice. But the evil program can still steal the data. Well, let's fix that. And to do that, we set the evil program's segment before it's run. And after it's done, we reset it. Then we also set the address in the evil program's linker file to 0, and we're ready for testing. So let's run the kernel and let's take a look at the file where the evil program stores the stolen data.
and it's empty, so the evil program wasn't able to copy. But wait a minute, didn't we say that the CPU raises an exception when a program tries to access memory outside its segment? And we didn't implement a handler for this type of exception yet, so the whole kernel should crash. Well, that's strange. Let me tell you, that almost drove me crazy. Why doesn't it crash? Well, apparently QEMU doesn't emulate all of segmentation if we don't explicitly activate it. And even then I had problems to get it running. So let's switch to another emulator, namely Box, which we've used before. And then let's try again. And oh my god, that's exactly what we expect. But to be sure, let's take a look at the logs. And here we see that the exception indeed was raised because we tried to read beyond the limit. And all what comes next are errors resulting from the missing exception handler. We just successfully implemented memory protection. I think it's so cool to see that in action. Anyway, that's it for this video. See ya.